So I need the permission to share the screen. Hello, Mr. Hasi.
Yes, sir, you can start.
Yeah, just is it visible? Hello, is it visible? The screen is visible?
Yes, sir.
Okay. So thank you very much for giving me this opportunity, and please keep on asking the questions as and when it comes. And so I'll be sharing with you latest technology, what is there with Nikon as well as in the market. And as far as the optical microscopy is concerned, so let's start. Let's make it more interactive. Just keep asking the questions whenever you think of. So my name is first of all MS Tanwar, and I'm taking care of application and product all India for Nikon, and I'm associated with Nikon since 25 years now. And so let's start. I'll be talking on two topics. One is, of course, fluorescence and confocal microscopy, as well as super resolution microscopy, what is beyond confocal. So let's start with that. So basically, the content of this particular presentation is what is confocal and how it is different than fluorescence microscopy. And I think everybody who is there on this platform are using a fluorescence and confocal both. So may not be very difficult to understand. And basically, what are the new technologies for dynamic analysis which is being implemented in latest confocal systems, and what are their application capability and why those features are implemented for new capabilities of the system. First, let's understand what is a confocal. So basically, when we talk about confocal, so we think about 3D imaging. We talk about optical sectioning. Thick specimen needs to be captured. So how do we do that? Basically, optical section can be captured in both wide field. When I'm saying wide field, it is a fluorescence microscope. Confocal is a confocal. So wide field means here when I'm saying wide field, please consider it as a fluorescence microscope. So optical section can be captured in both confocal as well as wide field. So let's say what in a confocal happens. So in a confocal, when the illumination is coming, illumination first of all in confocal will always be a laser based, depending on your dye, what you are using. So the excitation needs to be selected. Let's say if it is DAPI, you want to capture a nuclear staining. So definitely you need to use a 405. These are defined wavelengths. GFP, you need to use a 488. Let's say RFP, you need to use a 561. Sci-fi, you need to use a 640. So these are defined wavelengths with respect to the dyes, which has some kind of excitation, peak excitation. So you need to, there is a chart available on the website for this, which laser excites which dye. So that is there. So in this case of confocal, the illumination will be a point source, which is a laser base. And if you see, it is hitting the dichroic mirror. It is hitting the dichroic mirror through the different mirrors. It is going to the sample, and the emission is coming back to the same dichroic mirror. It is going through a pinhole to the detector. So this pinhole is basically rejecting the out of focus light and allowing only the light which is in focus to the detector. Now this is a detector. Detector is detecting the emitted signal from the sample. So detector can be many types. I'll explain you. It can be a PMT, photomultiplier tube. Then PMT can be a type of gas, gallium arsenide phosphate detector. So this is how a confocal works. It's a point illumination. Then it is hitting to the dichroic. Two different mirrors. It is going to the sample, and emission is coming back to the same dichroic mirror. And to the pinhole, it is going to the detector. Now, in a wide field, a fluorescence, what happens? In a fluorescence, first of all, the illumination changes to LED or a mercury lamp. The same concept is there. It is hitting the dichroic mirror, and through the lenses objective, it is going to the sample. The emission is coming back to the dichroic mirror. It is getting detected by a 2D detector. 2D detector means a camera, SCMOS, a CMOS, or maybe an EMCCD camera. Anything can be taken care. Anything will be able to capture the image of a fluorescence microscope. But here we are not using a PMT. So the biggest difference between if you see these two things is pinhole. So in a wide field, there is no pinhole. So what is happening? All the out of focus light is being captured by the detector, which is a camera. So what it will do basically? So the image will be having a lot of out of focus information. Image will not be very clear, not very crisp. But in case of confocal, the image will be very crisp and the background will be dark. So as it is eliminating the out of focus light. So that is the capability of a confocal, and this is a major difference between a fluorescence and a confocal microscope. So any issue till now? Is it easy to understand?
Good afternoon, Mr. Tanmar.
Hello, sir.
Sorry, I
Yeah,
was late to join.
no problem.
I was not able to introduce you, but for
Always.
other participants, you are very lucky that Mr. Tanwar himself is here. He is one of the, very knowledgeable persons in India who knows about all about confocals and have been in this field for years now, and have been always a good friend of us. And whenever we wanted, he has always helped out. And moreover, in this regard, what he has explained till now, I would just, for students' benefit, I would just ask you one question. So, what happens if we put a pinhole in a fluorescence microscope? Does it become a
Absolutely.
confocal?
So yeah, so basically it's a very good question. So basically the it will definitely eliminate the out of focus light, but the only thing is this: as a laser has a better penetration capability with respect to LED or maybe a fluorescence light. So that definitely difference will be there. But
Yes, so
definitely you will be able to.
whenever you introduce a pinhole, the light source will never be bright enough that
Of
it
course,
can actually give you such images like confocal,
correct,
right? Because it
correct.
will be very, only a subset of light you are allowing.
Absolutely. Yeah. And because see what is happening in a point source, it's a point source. Means it's basically a very, very precise point laser. That's the reason why the laser is used in this. And in case of wide field, of course, it's basically illuminating whole volume of the sample. So that is the big difference, illumination. But definitely there will be an improvement if the pinhole is placed in a wide field microscope. There will be an improvement, but not as respect what it is coming up in the confocal, because the laser is also a big difference. The penetration capability and the point illumination is very precise in case of laser. Yeah.
Okay.
Shall I go forward?
Anyone has any other question? If not, maybe we can go
Okay.
on.
So in case of confocal, of course, we can capture optical section. That can be done in wide field also. As I said, it just need a motorized D. Any microscope which has a motorized D can capture an optical section. But of course, the clarity, as we said, in a confocal, which will be much better as compared to a fluorescence microscope. So you can then perform a 3D reconstruction using a volume feature of a software. So this is the difference between wide field and confocal. So the background is pretty dark. And of course, the PMTs or the photomultiplier tubes, these are also playing a very big role in this. Basically, you have a very dark background because these detectors are capable to capture a single molecule fluorescence image. But at the same time, these days, when I'm talking about the cameras have also come up in the field of microscopy, which can perform single molecule fluorescence imaging, which has a QE of around 95%. So we call it as an SCMOS camera, scientific CMOS cameras. They are also being used as a single molecule fluorescence imaging. So we'll come on that later. So this is the difference between wide field and a confocal. But in confocal, you can perform multicolor imaging. When I'm saying multicolor imaging, as I said, confocal has a photomultiplier tube. So number of the detector will decide how many colors you can capture. Let's say if it is a filter-based system, so if you have a 4 PMTs, photomultiplier tube, you can capture 4 colors simultaneously. In case of wide field, the number of the cameras will decide, but normally it is what users are doing simultaneously. Let's say maximum 2 cameras can be attached. But these days there are attachments wherein you can perform optical splitters in front of the cameras, wherein the camera sensor, let's say if the sensor is 2K by 2K, for an example. So you can capture even 4 color in that, but the 2K by 2K will become 512 by 4 images. That means 2K will be divided into 4. 512 will be the one image, and then the image size will be reduced for sure. The resolution will be reduced. So you can perform 4 color, but then it really needs a very precise alignment between each image. In case of confocal, there is no issue. 4 detector will capture the 4 color. If it is 2 detector, will capture the 2 color. So that's another difference between the multicolor if we talk about. So in case of confocal and fluorescence, when we talk about magnification, in case of confocal, the magnification can be changed by the scan zoom lens. So there is a zoom lens. So let's say if you're working already on 60x objective, and if you want to zoom a particular area, so that is possible in confocal because there is an optical zoom capability. But in case of fluorescence microscopy, let's say you are working on 60, you can maximum go to 100. But if you want to project or zoom a particular region of interest, that is not possible in case of fluorescence microscopy. There is no optical zoom after 100x. And to be very precise, there is no ROI capability, basically, as compared to what confocal is giving in terms of optical zoom. So there is no way you can, zoom optically to a particular ROI in case of a fluorescence microscope. But in confocal, you can do that. Let's say you have a particular region of interest. I want to zoom this particular ROI or this particular cell to the maximum optically. That can be done in confocal. In fluorescence, not possible. It can be done digital zoom. Then digital zoom will have a pixelation. So that's not possible in that. So brightness in case of confocal can be increased or decreased by the pinhole gain. Sorry, by the PMT gain, which is photomultiplier tube. And in case of fluorescence, you need to change the exposure time of the camera. Color, as I said, you can perform multicolor based on the number of the detectors what you're using. In case of fluorescence, it's either mono, 1 color, or 2 color. You can perform 4 color, but then you need to reduce the resolution. Region, as I said, you can perform imaging just on point, just on line, and just on ROI. Those kind of controls are not there in fluorescence microscope. So you cannot perform just a region of interest, as I said. If you just want to perform some line profiling, just on a particular line, you want to do the imaging, that's not possible in fluorescence. In confocal, such kind of things are possible. Yeah. So let's come to a new generation of systems, how they look like, why they have been designed like that, what is the need of those systems to be designed like that. Till now, is it okay? Or am I going very fast or it's fine?
I think this is
It's
okay.
okay, sir.
Students, please speak up.
Yeah. So let's understand what is new and why it is new and why it was introduced. So of course, so Nikon has the base of the confocal will always be an inverted or an upright microscope, depending on application. So the microscope, as this is shown, is the inverted microscope, and the microscope is required for any confocal because confocal scan head will be attached to a microscope. A microscope is must for any confocal. So of course, microscope has many features. The latest development is basically the world is going towards very large field of view. I'll explain you why large field of view. So this particular system is having a very large field of view, image capturing capability. So let's say this is an 18 field of view. And for an example, this is a sample which is captured. This is a sample which is captured 18 mm. So 22 mm, that means we have captured a wider area. You see, 25 is more area with respect to what 18 mm was having. So let's say if we want to capture a model animals or tissue sample, which is basically a large. So if we have to capture with a smaller field of view, you have to stitch the sample. Stitching means more time, more exposure of the laser on the sample. That means more photo bleaching. A large field of view will capture will require a less frame to cover that whole sample. And also another benefit of large field of view, I'll explain after this slide. Then these days, confocals also come with, of course, because confocals are not just to capture a beautiful pictures, they are also being used for time-lapse imaging, lifestyle imaging, long-term lifestyle imaging. Now, the biggest problem with the long-term lifestyle imaging is focus get drifted with time. That means, let's say you have set up an experiment for 24 hours, and or maybe few hours, 2 hours, 3 hours, whatever time you want. So what will happen? The focus will get drifted with time, and that will happen because of the two reasons. First, the temperature of the room changes, and secondly, if somebody just barged in the room through the door, that will change the pressure of the room. So that will affect the sample focus. So with time, the focus will get drifted, and at the end of the day, you will see that my sample is not focused, and the lifestyle experiment just got waste. So to take care of those situations, so these days the system comes with a focus correction system. So what is happening in focus correction systems? So basically, there is an LED which is basically checking the cover slip distance, and if there is any change, that is giving a feedback to the sensor. So that sensor is taking care of the offset lens to compensate the loss of focus. So this is happening based on continuous optical feedback. So you don't have to worry about long-term lifestyle imaging, irrespective of the time what you have set up for long-term lifestyle imaging. You don't have to worry about that. So you can keep going on lifestyle imaging. You can keep performing without having an issue of, let's say, temperature or the pressure change. System takes care of this. So these are the technological advantage and development these days happening. Secondly, the microscopes are built in such a way, because microscope is just not, a standard usage of microscope. These days, microscopes are also being used by many people, especially in IITs, who are developing something own optically. So they definitely need a back focal plane image on the screen to check and confirm whether the laser is perfectly getting aligned or not. So if you see the right side image, the green circle, so this is a Burton lens. This shows this projects the back focal plane on the eyepiece. Back focal plane means where the objective is getting attached, basically under the nose piece. So there, the laser where it is falling needs to be confirmed. If the laser is falling at both the periphery, in the first image, if you see the green circle and on the right circle, there's a bright spot. So that means it is confirmed that it is verified that the laser is falling at the both periphery. And these are technologies which is called total internal reflection fluorescence. It is for the confirmation of that. So these are the technical advantages of these microscopes. So it's not restricted to just capturing images. So these microscopes are built for multiple applications in addition to just the standard imaging. So that is advantage of this system. Now, these days, what confocal can do besides just capturing nice images? Confocal can go much faster because, of course, confocal these days they are catering to the wide application capabilities and wide requirement of the users. So some users may come for, I need a good image. Okay, confocal can do. I need a deep image. Okay, this confocal can do. I need a fast image. I need a gentle image. I need to do a long-term imaging. I need to do a calcium imaging. So those kind of wide answers. So these days the confocals are built based on that, not restricted to just one application. So basically, these are the various capabilities of, like, system must go fast. I need to, perform dynamic experiments. System must do deeper imaging. Those kind of like a brain sample. So must do a gentle imaging for long term. So these are the different capabilities the systems can do. So let's see how it do. So Nikon has now released the AX system, which is the latest in the market. So I'll explain you what is the technological advantages, so why it was built. So first major capability, what the basis of the system was based on the survey done by worldwide. Everybody wanted a wide field of big field of. Now, it was not easy to develop these kind of systems because wide field means changing the whole product in terms of mirrors and also basically the tube length of the microscope, which is difficult. So also the mirrors inside the confocal, which we call it as a galvo mirror, they need to be bigger. So to make those mirrors bigger and aligning everything together was a challenge, but definitely Nikon built those systems. So the latest system comes with the largest field of view in the world, which is 25 mm. Now, it's just not a feature. There is a reason behind it. Why. So if you see this image left and right, so user has captured this whole image in one shot. Had it been a smaller field of view, you need to capture 2 or 3 frames. It must have taken time for that. And of course, the exposure of the sample again on the same area or maybe the same sample may have developed the phototoxicity. So for that, microscope and confocal both needs to align together and both needs to be having a 25 mm field of view. So both should have a large field of view, and Nikon made that. So more information than ever. So if you see this is 18, so diagonally if we see it's 25 mm field of view. So large field of view. Now, what is so good for large field of view? Besides saving time, if you just see this, when I'm saying saving time, if you compare left and right image, 25 versus 18. So this is how the image is being captured and stitched, and that's still going on. So if you're doing a lot of imaging, so you will save a lot of time. Now, other than saving of time, what is the other utility of the system? So other utility is confocal images are used, and confocal is performed basically to do a quantification, right? Quantification is the key. Besides getting just good images, we have to do an accurate quantification. So if the quantification is done based on the large field of view, the statistical accuracy will be much higher. So let's say with respect to the whole sample, if you are using a wide field of view, a bigger area of that whole sample for the quantification, the statistical accuracy will be much higher as compared to the smaller field of view. So because you are taking estimation based on large field of view. So if you see with respect to 18 mm and 25, the 25 mm has a better accuracy as compared to a cell count in a shorter time as well. So this is a capability and advantage, application advantage with respect to the research of a wide field of view. So this is a very strong capability. And this is basically the cell count, cumulative cell count versus field of view. So if you see the red line, its cell count is higher as compared to smaller field of view. So that is an advantage. Now, Nyquist sampling for high resolution capability. So basically, when we talk about how to measure the resolution, this is the formula. So we have to have a 1 point. So R is basically resolution 1.22 multiplied by wavelength by 2 NA. NA is numerical aperture of the objective, and that's how you can perform the resolution of the. You can count the resolution. You can calculate the resolution of the optical microscope. So we'll come on the resolution when we come on the super resolution. So basically, what is Nyquist sampling? Nyquist sampling is very important part of any image, and that is required when you are sending the images for publication. So basically, when a system is capturing an image, the representation is from analog to digital space so that our system or our eyes can understand that. So that needs to be sampled around 2.3 times. That means image needs to be at least 2.3 times smaller than the object that is being resolved, which is very, very important. Pixel size into 2.3 is equal to the resolution of the objective. So that is very important to satisfy the Nyquist sampling. These days, the systems are automatically doing it. You don't have to do anything. So if the Nyquist sampling is not done, that means the resolution is not proper. So you will see these pixelation, right? So, but if the Nyquist is satisfied, the system will automatically take care of that, and you can see the image clear. right? So these days systems are coming with the automatically, which can take care of the Nyquist sampling. And the system is basically up to 8K by 8K resolution now these days. That means a very high resolution is possible. So these are the different example of resolution. So 512, 1K, 2K, 4K, 8K. But let's say if I want to zoom this particular red region, this one, extreme right, this red region. And if I'm capturing this red region, this whole image using a 512, I want to zoom it. So what will happen? Let's see. So if you see this, yeah. So if you see from left to right, if I zoom that 512, that particular area with respect to 8K resolution, of course, 8K is much clearer. So because I have captured at a very high resolution of 64 million pixel, and my system is capable to satisfy the Nyquist when I'm zooming it digitally, so the image extreme right is much better as compared to the 512. Because 512 enough pixel were not there. When we zoom it digitally, it pixelates. So this is the difference. So system has a various capability of resolution from 512 to 8K. You can capture depending on the requirement. So this is an example of a neuron image. It's a huge image captured in a very less time using a large field of view. If you see this, of course, it's stitched, but took a very less time. So this is a whole view, right? So these kind of samples you can image very, very fast using these systems. So now these days the systems, as I said, the systems are built for a more central facility, like which can cater more wide application. So as I said, somebody will say, I want to do a fixed imaging, fixed cell imaging. Somebody says, I want to do a fast imaging. So fast imaging, you need some kind of a fast scanner. So the systems are coming with a hybrid scanning technology. So we call a high-speed scanner as a resonance scanner, and we call a high-resolution scanner as a galvo scanner. So resonance scanner are capable to capture the fast imaging, a dynamic experimentation at a much faster rate as compared to a galvo scanner. Galvo scanners are for high resolution. Resonance scanners are for high speed. But definitely, when the speed goes up, the resolution brings down. It goes down. The image quality may go down. And if the resolution is high, the speed is low. But
Can you
in case of
just a little bit explain the difference between Galvo and
yeah, yeah.
resonance scanner?
So yeah, so galvo scanner. So basically, when we are scanning, as I just showed in few slides back, so there's a 512 by 512. I was talking about 1K by 1K images. So there are two mirrors which are always moving at a particular frequency. In case of galvo, they move at a 2K frequency, so the movement is not very fast. So in that way, what is happening? One mirror is basically writing at in the x direction. One mirror is writing on a y direction to create an image. So that is basically a galvo mirror. And in case of resonance scanner, one mirror of galvo is fixed use. They will be using one mirror of the galvo and one a separate mirror of high speed resonance scanner, which moves at a speed of 8 kilohertz. That means very high frequency, and it writes at a very high speed. Now, it is basically both are built into one box, one scanner. We call it as a hybrid. So depending on what is the usage of the user, you can always switch using a software to use a high speed or a high resolution. So this is basically a mirror movements, which makes it high resolution or high speed scanner. So of course, the mirror for Galvo is X and Y both movement. In case of resonant, there is basically one fixed and one movement. So those are the two technologies which is built into the system as a of course as an option depending on the usage. So resonance scanner recently have been increased to up to 2K by 2K resolution, which means with high resolution you can capture a very good quality of data, speed as well as field of view as well as high quality of image. So you can capture all three. As I was saying that if the speed is higher, the resolution and of course the image quality will deteriorate. But in case of this system, the field of view, will remain 25. The resolution will be quite good, 2K by 2K, and the image quality will be also very good. So these are the two images which is captured, one by resonant and one by galvo, almost same. So that means that the good part is you will be saving a lot of time because the speed is high. Of course, the field of view is pretty big, and the image quality is almost like a galvo. So very good capability of the system. And we recently installed the system in NBRC, large field of view and high speed scan 2 weeks back. Yeah. So if you see left hand side is resonant and right hand side is galvo, almost same image quality, but the benefit is with the left one you will be saving a lot of time, and field of view for both field of view is same. And if you're saving good time and getting good image, why not? So that's the capability of resonance scanner these days. So this will be helpful in many applications. So if we talk about resonant and galvo, if you are seeing, let's say, if you see this circled white and yellow, so below one is the resonance scanner and above one is the galvo scanner. If you see in the galvo scanner, the scanning is slow. So if the scanning is slow, the pixel dwell time will be lower. That means what I'm saying with respect to pixel dwell time means how much the laser is residing on each pixel. That means the pixel dwell time. If it is more, the scanning will be slow. In case of resonance scanner, as the frequency of the scanner is very high, so the pixel dwell time is low, but resolution definitely is increased. So if you see above and below, the white circled image is basically getting bleached with time because the pixel dwell time is pretty high, right? So the laser is residing on a pixel for more time. The time is more. In case of resonance scanner, if you see, the bleaching with respect to above is much lower as compared to the galvo. So this means the resonance scanner can be very good tool to perform long-term lifestyle imaging with a less phototoxicity. So less bleaching. If you see this rate of intensity drop in galvo is much higher in 15 hours with respect to resonance scanner. So resonance scanner can be used for long-term lifestyle imaging and while maintaining the speed. So as far as the speed is concerned, so galvo speed maximum is 240 and a resonance scanner is 720 frames per second in a resonance scanner. That makes this product as the fastest confocal currently in the world. So these days, these applications are required for capturing many fast dynamics. Now, there are some advanced applications which you can perform. So you must have heard about FRAP. FRAP is fluorescence recovery after photo bleaching or photo activation, photo conversion. So you can perform these real-time dynamic experiments with the system. So you can always have an additional scanner wherein one scanner will perform the bleaching. Now, why do we do bleaching in a sample? Though maybe I can explain this much better maybe tomorrow on the system. So, but definitely bleaching is, FRAP is used for diffusion studies. Diffusion, let's say how we do it in a sample, let's say it's a live sample and we make a region of interest, ROI, and we bleach that particular region of interest, that background will become dark. If the background will become dark, so definitely the intensity will be 0. And let's say some proteins are moving in that dark area and moving and the intensity will start going up. That means the diffusion is happening once the intensity goes up. In the sample, the diffusion of the proteins is happening. So this is the study which we can perform using a FRAP. So to perform the real-time FRAP, you can add one more scanner and you will not have any delay with respect to bleach and image. So the time when you're bleaching the sample, at the same time you can image simultaneously, which makes it to real-time application capable system. So similarly, photo activation is there. Photo switching is there. Photo switching means basically the sample is basically changing the color. If you see this sample getting green once 405 is hit on, so it is activating the protein. Let's say PAGFP, photoactivable green fluorescence protein. Those kind of experiments can be done in real time. This is photo conversion. It is getting red. So these are the real-time experiments what you can perform. As I was saying, confocal is just not limited to getting good images. So it is basically doing many things. So now, as I was talking in the first few slides about detector, so these days the detectors, the class of the detectors have changed, and these are the type of PMTs. But of course, the quantum efficiency have got increased. Quantum efficiency, we call it as the amount of signals what they can capture, what they can retrieve during the emission of the signals from the sample. So the GaAsP is gallium arsenide phosphate detector. These are the new detectors in the market, and these are having a quantum efficiency of around 45% in around 500 nanometer or 530 nanometer wavelength range. So very sensitive detectors, and you can capture a single molecule imaging also with these detectors. So left hand side is a conventional, and new is the right side. They are just showing the darkness uh, at the background. So it's quite sensitive detectors. Now this is how it looks like. So these are the box. So if you see, these are the 4 PMTs, and there are 2 types of detectors. One is, if you see this left hand side diagram, there are some wheels. So these all are filter based imaging, filter based detector. That means in front of PMTs, the filters are there with respect to what sample you are capturing. Let's say if there is a DAPI. So the DAPI filter will be moved as far as the emission is concerned, and it is giving the signal to the detector. But in the right case, if you see, there are 2 wheels only, and there are 2 spectral. That means those slide kind of a thing. These are spectral. Spectral is basically filterless. So you can select the bandwidth of the sample, and in a very precise emission range, you can capture the data. So these are very flexible. So you can perform multicolor imaging using even one detector, but of course sequential. So, but you can perform 5, 6, 7, 8 colors sequential image. Sequential means one by one. Simultaneous means all the detectors are working simultaneously and simultaneous imaging. But there is a trade-off. If you are going for simultaneous imaging, there is a possibility of a bleed through. But if you go with the sequential scanning, the bleed through possibility is less. Sequential is one by one. So spectral. So if you see, the first and the third one is a spectral. So there is a flexibility of selecting the bandwidth in what spectral range you want to capture the data. So that's possible in this system. So these are the things. So then confocal is just not restricted to, uh, just to capture, as I said, images. Of course, the resolution of any optical microscope or confocal is around 240 nanometers. When I'm saying resolution, I'm not talking about filling up of pixels. I'm talking about how well they can separate the 2 points as the 2 points, right? So in case of confocal, these days the confocal capability is also enhanced. So confocal can be used as a super resolution tool. So in a confocal, without a super resolution capability, the XY resolution, XY means how well I can define 2 point as a 2 point, is 240 nanometers, and Z is around 550 nanometers. But when we apply a super resolution in a confocal, so you can basically separate the 2 dots or a 2 sample or a 2 protein around 120 nanometers, XY and Z around 300 nanometers. So this is the capability of, so they have shown the comparative. If you see, there's a left is a 3D sim. We'll come back on sim in the next presentation. And right side is confocal based enhanced resolution, and extreme right is one Airy unit, one Airy disk. So confocal, when we are performing a normal confocal, we perform at a one Airy unit pinhole size, which will capture the data as a standard confocal. But if we reduce the pinhole to 0.2 Airy unit, what is happening? It will improve the resolution, but at the same time, it will reduce the intensity. So as I said, these days the detectors are highly efficient, and we can increase the gain of the detector to compensate the loss of the intensity, because if we increase the laser power, it will induce the toxicity on the sample. So we choose to increase the detector gain and then applying the denoise factor, because when we increase too much gain of the detector, the noise possibility is there. But we implement the denoise factor so that we can reject the noise and actual sample will be there. So if you see the extreme left and middle one, they are almost same. So we are talking about maybe 120 nanometer capability of the confocal. So we can improve the resolution of 120 nanometer. And extreme right is roughly around 240 nanometers. So this is the capability of these confocal these days. You can enhance that. So they've compared with various systems like Eriscan, and of course STED will come on that, and of course Nikon enhanced resolution. So these are the capabilities. So, and software plays a very, very important role these days because you need to do capturing, you need to perform quantifications based on what exactly applications you are doing. So everything can be done on these. The customization of the experiments, any conditional experiments you can perform. So maybe we can talk this tomorrow on this. And also you can build your own experiments. So this is like a calcium flux. At the same time, experiment, and at the same time, you can analyze your data on the fly. So these are the possibilities with these days. Powerful softwares are there as a standard. So you can customize, you can perform these high throughput imaging, HCA, high content. So you can scan the whole well and you can capture the data in the well, each well, what way you want to go across, or maybe the well, how it is built. Any way you can perform the imaging in the 96 well. And also these days, many AI capabilities there in the confocals. And when we are saying AI, that means no more, you don't have to set up the laser power or gain. You just click one button, automatically it will take care of those. So there's no saturation. So normally these days in a conventional system, what you're doing, you are basically setting up the laser power, gain, and switching on the saturation indicator, which I will explain you tomorrow. And then you're setting up the laser gain so that sample is not saturated. But with auto signal AI, you just click one button, so it automatically takes care of the power and the gain, depending on what kind of sample you are using. So there is an option of whether it's a live cell, stable sample. If you select that, system automatically knows what to do. So many AI functions are there. Now, let's say this is the DIC image. It's very difficult to, let's say, count the nucleus because that software basically performs based on intensity. But here with the AI, you can perform these kind of capabilities also. Let's say the sample is very, sometimes it's a very low light fluorescence, old sample, and you want to enhance. There's a lot of background, so you can remove the background using an AI. And sometimes you want to count the processes. If you see these processes, it's very difficult to count. So those can be done using a segment AI. You want to do denoise. Let's say this is a very noisy sample. You can remove the noise and enhance the sample. So if you want to do, this is for a wide field. If you do a lot of, let's say, wide field imaging, you can also apply AI on that. So if you see this, left is a wide field image. And when we run through a Clarify AI, it works. Out of focus light is removed. So these are all algorithm based. As I mentioned about the lasers, so laser lineup is this one. So as I said, so 405 good for CFP, hex, and also DAPI. 488 is good for GFP and also YFP, FITC. And 561 line is good for your RFP and TRITC, Alexa, 594, Micro Tracker Red, M-Plum, M-Cherry, and 640 is good for Sci-Fi. So this is just a summary. Of course, a wide field and the speed is necessary these days. And of course, the sensitive detectors are there these days. So this is more on confocal. So now I want to start a super resolution. Is that okay, sir? Any question?
One basic question from my side, actually. So, just give me a moment. This is can go with a very nice question. So, can you tell me the basic of fluorescent dyes? So these dyes are normally they illuminate when they are binding something. Suppose I'm using mito tracker, and I normally what we do, we put that dye which is going to bind the mitochondria and then fluoresce. So the dye that is not binding, they never fluoresce.
No.
Right. They would never fluoresce. So
they will never.
Why does that happen? Because the fluorescence is intrinsic to the dye. So why
Correct.
that does
So,
not?
so there may be a possibility that, let's say, if it is not binding, it may autofluoresce also.
Yes, why normally that does not
Yeah,
happen?
yeah, yeah. So basically, if it is not binding somewhere, but definitely it will definitely have an effect on the image. So for that, as I was talking about spectral, right? So these are basically uh, unwanted signal which is coming in from the sample, like some plant sample are there. There is a natural autofluorescence, right? So using a spectral, so spectral has a, when we are talking about the spectral system, so spectral, when we are going and checking the fluorescence and making an ROI, so it will show multiple profile. It will not show a proper peak. Proper peak means signal. If it is showing a multiple profile, we can always minus from the main signal.
So
So for that, yeah,
a similar question. Now I have a dye. Suppose I have conjugated that dye with a nano particle, which we have synthesized, and we actually chemically cross-linked that with a dye, fluorescent dye. Now I am treating with that nanoparticle. I want to see whether that nanoparticle is inside or outside. Uh,
how you can see that.
so can we do it in a confocal? Because
Of course.
outside, no, my question is the nanoparticle, suppose I am giving it in a crude method, like I'm putting it on a leaf or something. Now, there is something on surface, there is something on outside, they will also fluoresce. Or you don't think the only thing that is inside will fluoresce?
No, no, definitely. That's what I'm saying. So spectral will be helpful for that. If it is basically unnecessary emission, or maybe the autofluorescence. So definitely that can be rejected using a spectral, but you definitely need to capture an optical section to see inside and outside. And wherever it is capturing outside, so those signals needs to be rejected using a spectral detector.
Okay. Okay. Hmm.
That is
Good. Oh.
possible.
Hmm.
That is possible. So now we'll just go to any other student who want to ask any question.
Students, any question? Not here at the moment.
Okay,
Go ahead.
no problem. So I will share. Just so this is the next topic. So we saw fluorescence and we saw confocal. Now what is above than that is super resolution microscope. So there are various methods, and why do we need a super resolution microscopy? So to resolve better. When I'm saying resolve, as I said, to see how well I can separate out 2 points in the 2 points. So the topic of this presentation is super resolution microscopy, breaking the optical diffraction limit. Now, what is optical diffraction limit? The optical diffraction limit is the capability of the optics wherein they cannot resolve better than some numbers. They cannot resolve better than that. So in case of optics, the optical diffraction limit is 240 nanometer XY, and Z is around 550 to 600 nanometer. You cannot resolve better than that in by just using optical microscope. So you need some processes to improve the resolution. How we do it, that I'll explain. I'll try to explain. This is very much physics, but just stop me wherever you want. So yeah. So again, we see the microscope is important for a super resolution also. So a microscope will remain same, inverted microscope in this case. And first, let's see what are the major approaches towards the super resolution in the market. So one is SIM, structured illumination microscopy, and of course, which is getting now less popular as confocals are getting more in the market in terms of super resolution. They are basically advanced so much now, and I can explain you some advantages and disadvantages of SIM and why it is going off the market and why confocal is getting in more as far as super resolution is concerned. Then another is STORM. STORM is stochastic optical reconstruction microscopy, and PALM. PALM is also similar localization microscopy, photoactive light microscopy, we call it as a, and of course TED. So these are the three major approaches for a super resolution. And let's see, so we talk here about SIM and STORM majorly, and let's see how they work. So this is an microscopy scale. So up to this, that means around 240 nanometer or so, light microscopy works. When I'm saying light microscopy, it's a wide field microscopy as well as a confocal microscopy. So if we want to go to a subcellular level, we need a super resolution. So we are talking somewhere around 20 nanometer. In the range of XY, like 20 to 120 nanometer, and in Z, around 50 to 300 nanometer in Z. So in case of cellular level, so we are okay with a confocal or a wide field microscope, which is 240 nanometer. So of course, again, this is the same formula. So let's say when we talk about sub-resolution lights, so airy disk. Airy disk is basically, if I just talk about in a simple language, so when we have any light, so we take a torch and we, let's say, project that torch on a wall, and we see many rings. So the innermost ring is having a maximum intensity, and it is good for providing the best resolution. And that is basically considered as the one airy disk. So similarly in optics, if you see the lower image, intensity distribution, the middle one is having a best peak. So when it is plotted, so that is called one airy disk. So the pinhole I was talking about in confocal, we used to set up at one airy unit, right? So in case of super resolution, so what is happening? There is a real space and there is a Fourier space. Fourier space is at the back focal plane. Real space is basically based on Fourier space, we can create a real space image. So first of all, let's come to a SIM. SIM is structured illumination microscopy. So it was basically developed at Max Gustafsson lab at UCSF, and unfortunately, he's no more. And but of course, he developed this technology, and then it was further developed by Nikon and Zeiss both, and based on their capability or engineering level. So they have implemented, the principle remains same. So we talk here about more principle, how it works. So SIM is basically fast and less phototoxic for the lifestyle. But the biggest drawback of SIM is it's not for the deep imaging. When I'm saying deep imaging, it's not more than, hello. Just, hello.
Go
Can you hear me now?
go ahead, yes.
Yeah. So when I'm saying deep, just a minute, sir, just a minute.
Rasmi, do you have any question? There is noise coming from you. Okay, no. Go ahead.
Just a minute. I think, is it a visible presentation or no?
Yes, sir. Very much visible.
I don't know. I'm unable to see that. I am unable to see. Okay. Is it changing?
Yes.
Okay. So, SIM is basically not meant for a sample which is more than 25 micron or maybe 30 micron. So it is not meant for. So the XY resolution of SIM is around 1.1 to 115 nanometer, and in Z it's around 270 or 269 nanometer. And there is a mode called a TURF SIM, which is for single molecule fluorescence, which is around 85 nanometer XY. So when we talk about, let's say, for an example, there are two dots and two peaks I can see. The distance is around 750 nanometer. If I'm bringing it closer, 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 distance is 350 nanometer. Further close, 250 nanometer, I can still see the two peaks. But here, at 200 nanometer, I cannot see the two peaks. It's one. That means this is the optical diffraction limit. So my eye cannot differentiate less than this. So we need certain process. What to do with that? So we will come on that. So this is the formula. I've already shown you how to calculate the resolution. So super resolution is a kind of an optical process which has some special process in addition to the optics, basically, and how they improve the resolution. We will just go in that. No special sample preparation is required for SIM, not needed. Whatever you're using as a conventional fluorescence or a confocal, that will work for. So NSIM. So just to share some images. So this is left in is a white field image. It's a mitochondria. Here you can see crystal around 100 nanometer, very clearly, very well defined. You can separate those. So conventional left-hand side, this is SIM. You see very fine actin filaments, very well resolved. And this is confocal, 4.2 zoom, and this is SIM. Nicely resolved those filaments. And if you see left confocal and right SIM, again, you can see very nice resolved. Even the DAPI is also resolved quite well. And left and right side is a white field turf, and left hand side is a turf SIM. Nice, yeah. So now let's go to a principle. So this is more physics. Just stop me if you're not understanding. So we need to understand a special frequency, imaging theory, and Fourier transform to understand the SIM principle. So let's say, what is special frequency? Special frequency is lines per mm. So these are the boxes 1, 2, 3, 4, 5. So this is 5 lines per mm. This is the special frequency of this period. Just understand, just remember this special frequency, lines per mm. So let's say we take an example of special frequency. We take an example of diffraction angle in the optics. One example, we say small, medium, and large. So let's say if we shoot the light, so light is having a multiple orders. Zero order, which actually has a conventional information, and super resolution and a high resolution information will always be there in the first plus and minus order. So the diffraction angle is like this if we have a medium special frequency. If we have a small, so still it's okay. But if we have a high special frequency means you have a lot of information in the sample. But what is happening in case of high special frequency, extreme right image, the information of +1 and -1 order is going out of the numerical aperture of the objective. Even if you take a best numerical aperture like 1.49 objective, still the plus and minus order is going out of the diffraction. So that is a big challenge. And how we can bring back this plus and -1 order into the numerical aperture so that like virtually we are increasing the numerical aperture. That is the whole plan and whole.
So I have just one question here. So is that true that the plus order, +1 order, and -1 order, and the zero order, they have different angles of refraction?
Correct. Yes.
Okay. Okay. It's not
So,
as a whole a light has a
no.
particular angle of.
No.
And if I think it in a 3D or things like that, so anyway, the light coming out of a sample will become a circle or a cone, and plus order and +1 and minus order will be outside of the cone or outside of the circle.
No, so basically when it is going through some frequency, then it is basically, if you see the light is coming in the blue line below, and then when it is passing through some frequency, it will have angles, diffraction angle, right?
Yes. So but one particular light of one particular frequency, I'm not talking about the spatial frequency, I'm talking about the frequency of the light. It will have like different refraction angles, you want to say.
Right. Yes.
And because it is wider, then
of course,
good
wider,
NA,
that's why we are correct.
Good NA will not work. Even something that is going very close to the object, it will not work.
Correct. And our challenge is to bring back this information in the NA.
Okay.
Right. So that is how, and how it is being done.
So you want your objective to capture all those lost
information. Correct.
Okay.
Yeah. So how the imaging works basically. So let's say this is a high frequency example, and the illumination is hit. So this is objective diffraction angle. So this is coming basically in the objective end. So +1, 0, -1, everything is coming in the objective, right? But this is not a very high frequency. That means a super resolution information is not very high and everything is coming in. But so this is +1, -1, and 0 order is all in the objective. And everything is captured, interference happens, and the image can be captured. But let's say if we talk about a very high frequency, a sample which has a very high resolution capability, or wherein you can get a very, high resolvable image. This is a high frequency. This is how it is going on. Is this clear, sir? Now it is better.
Yes, yes, yes. That's why you need
No.
higher, even higher NA, but that is not
Correct.
possible.
Not possible. So virtually, we will. I'll tell you how to do that. So what is happening here? Only the 0 order is going, which is the conventional image. Basically, no extra information is coming. Our idea is to capture -1 and +1 inside. So now how we do it? So basically, every sample has some kind of a frequency, special frequency. And what we are doing, using a structured illumination SIM system, we implement a known frequency on a sample microstructure frequency. That means we have a known frequency, which is we have implemented as a human being in the system, which is basically a SIM high frequency. When we implement to the unknown, so these Moire patterns appear. If you see this spring-like structure, this appears. We call it as a Moire pattern, special frequency, right? So when we implement. Now, what is happening? We want to know what is the sample frequency, what is the sample microstructure frequency. That is our idea. Now, how we will do it? There is a mathematical calculation. One frequency we know. When we implement on the unknown frequency, so we'll have a total frequency, right? And from the total, when we minus the known frequency, we'll get the sample microstructure frequency. Now, how it happens? Let's say this is objective. So our plan is basically 0 order is going in inside, +1 and -1 is out, and there is a sample structure which has some frequency. We implement the structured illumination on that. And this structured illumination, how it works when we capture a, let's say, 3D image, it rotates basically 5 times in a 3 direction. 3 direction means when we are moving, let's say this is a sample, and we are moving 1 direction, 2 direction, 3 direction, so that the image which is coming behind the sample should also be covered. So we have to capture in a 3 phases and 5 images. So 15 images to capture 3D and 3 by 3, 3 direction and 3 images in XY, just 2D image. So I'll explain you how it works, what I'm saying. So when we are doing this, so this is basically movement of a grating. Grating means high frequency. So grating is known to us, which is a structured illumination, and there is a sample structure. So when we are implementing it, when it is moving, we are able to capture the first and minus order, first +1 and -1 order, and by mathematical calculation, we can input that thing inside the objective. So virtually it will look like we have increased the N of the objective. So this is a Moire pattern. So structural illumination is moved on the sample structure and using this formula, V3 is equal to basically total, basically minus the unknown frequency, we'll get, the known frequency, we'll get the sample frequency. So this is how we'll be able to bring back the frequency which is going out of the object. Now, how it works, basically, an image is composed of various variety of different waves. One wave, another wave, it's a merge of 2 waves. When we combine 9855 waves, it makes an one image. This is an imaging theory. And how it works in case of SIM, illuminate the sample with a known special frequency, a stripe pattern, right? It looks like, so if I take an example, if you see a door with some jali, and if you have some striped shirt, if you move in a different direction like this, you will see something is moving, right? So that's basically a stripe pattern movement and basically a high frequency information. So eliminate the sample with a known special frequency, stripe pattern. Read out the Moire pattern with 3 shifts and 3 rotates. Rotates it's a 2D image. And Fourier transform to the frequency space and isolate the first order using a software. That means isolate the first order high frequency information from the zero order, which is conventional, and then relocate using a software in a proper position. I'll explain you in next slide. An inverse Fourier transform will be done in a real space so that image can be created. So now how it works? Let's say in the first example, it's a sample, nothing is happening. At the back, there is a sample frequency, and at the top, the known frequency, which is positioned by us. It's a structured illumination, SIM frequency. Nothing is happening. So this sample may not have a high resolution information. But in the lower image, if you see, can you see these waves? Yeah. So it has a very high frequency. So the backside is the sample and front is the SIM frequency. So what we are doing in this case, we need to know the numbers of sample frequency. So that can be calculated. Total minus the node will be the sample frequency. Once that is there, so let's say this is sample and below the structured. So we have put a 3 shifts and 3 phase. So then we rotate the 3 direction. So what we are getting, so this purple shaped structure is what we have captured. The red one in the middle, is the conventional zero order. Rest all is plus and minus one order. So everything is collected using a software, then it is relocated based on the requirement, and then the sample, the high information can be placed and we can resolve it better. So if you see these kind of patterns we will see when we are capturing. This is the 3D image. 3D means 3D information is there. So this is 5 images and 3 rotation, 15 images. And if you see this is relocation by the software. So middle one is conventional, and this is all high frequency information at the surrounding. When we merge using a software, so we can see this as a Fourier, and when we do the Fourier transform, it can be changed to image. So this is conventional, and this is a super resolution image component, the peripheral one. So the middle one is a zero order, and rest is plus and minus one. So when we see, it looks like we have increased the NA of the object virtually. Is it understandable, sir? Or it's getting too much?
I mean, up to this is still okay. I mean, I know super resolution is difficult.
Yeah.
I do not teach it in class.
Okay.
So this is good.
Yeah,
it should be beyond something beyond the class.
yeah. So this is how then we can resolve and we can achieve and we can capture the high resolution image information, and we can resolve up to 120 nanometer in case of super resolution. So this is the Fourier data, and we call it as an FFT. So the more the better flower, the more the better image. So we can always check whether the image is super resolution or not using our software. We can click and check the FFT Fourier image. So if you see left hand side, FWHF full width half max is 290 nanometer in conventional microscope. In confocal, it is 210. But if we see through the structural illumination, we must resolve 130 nanometer. So this is how you can improve the resolution. This is how a super resolution SIM looks like. And the box is basically a windshield, so that no external light comes and no external air comes and disturb the sample. So the box is important. And there's a camera, inverted microscope. It's a camera-based system. And we call it as a wide field, but a super resolution. So you can always hook on with the confocal, but both are independent. So SIM is different and confocal is different. So SIM has various technologies or modes: 2D, XY information, 3D, XYZ information, curve SIM. If you just want to work on a membrane level. Membrane level means maybe above the cover slip, 100 to 150 nanometer if you want to work. So like vesicle trafficking, some membrane studies, turf SIM is a very good technology for that. Total internal reflection fluorescence based microscopy. So yeah, so this is basically capability of 2D and turf SIM. You can only work up to a depth of 5 to 10 microns. Above then you cannot do. the sample thickness should be just within 5 to 10 microns. In case of 3D SIM, maximum up to 30 microns. You cannot work more than that. So this is the big limitation of SIM, and that's why they are getting phased out. So just an example, conventional and SIM, you can see left and right, big difference. Yeah, so this is quite well done. You can perform lifestyle with SIM. And the camera used in SIM is basically, again, SCMOS, which is around 95% QE. And this is, again, a single molecule fluorescence cameras. So you can perform dual color SIM. And like this. So these are various objective, dual color, and lifestyle friendly, definitely, because the light is getting through the diffraction grating. So the power of the laser falling on the sample is less. Now, another technology, which is, as I said, which is getting in these days. So SIMs are getting out from the market, and what new is coming? As I said, confocal based super resolution means the user wants no restriction to the sample thickness. They want, okay, I should be able to use 6 samples also, but I need the same resolution. So now the confocal super resolutions have come in the market. So Nikon released recently in this February a confocal based super resolution, which is called SPPC based NSPARC, Nikon Special Array Confocal. So basically, which can perform imaging more than 100 microns and capable to achieve a resolution of around 100 nanometer, XY and Z around 300 nanometer. So what is so special? The best part of this technology is NSPARC is they have released a new detector which is called SPPC Special. It's a single pixel photon counter, and the background is very dark. It's a very sensitive detector. The quantum efficiency is around 65%. And if you see left and right image, the background is quite better as compared to left one. A lot of noise is there. So this is beyond gas. This is better than gas. So what we are doing, we are having this detector as an array of 25 detectors. It is not just one. So we have 25 detectors in which each element of the detector is 0.2 area unit. Now I was talking about 0.2 area unit. One area unit means a standard contour. But if we reduce the pinhole, it becomes 0.2 area unit. But the system when I was talking about in confocal session, that was more reducing the pinhole. You can increase the detector gain, you can improve the resolution, but that may not be good for samples when we are having a low light loss. That will not work. But here you can work with low light, you can work with bright sample, you can go for deeper imaging. In this case, each element works as 0.2 area unit, and then capturing the whole image with the proper brightness and using a shuffled summing up technology. There is a paper, pixel reassignment method. So if you see these different peaks, so at each 0.2 area units, the intensity will be different, right? Intensity will be different. Using a pixel reassignment method, they are correcting using an algorithm, and then everything comes to a same peak, and we can improve the resolution to 100 nanometer and 300 nanometer in Z. So this is the confocal based pinhole, and this is very well accepted now and getting good popularity over a SIM, majorly because of low light imaging. In SIM, that is also one big issue. So you need a bright sample in that. And of course, in this, you don't need a bright sample. It's fine, whether it's a bright or a low light. And you can go to more depth in case of NSPARC systems. So that's the confocal base. Now we come to the last topic, which is called STORM. STORM, we call it as a localization-based microscopy, stochastic optical reconstruction microscopy. Now the numbers when we talk about here is XY is around 20 nanometer, and Z is around 50 nanometer, which is considered to be one of the best super resolution in the market. And this was developed in Harvard exclusively for Nikon in Chavez Wong's lab. So you can have a 2D, 3D, and multicolor imaging with it. Now, how it works. So there is a lot of mathematical algorithm which is working on this. So I'll take an example, but this requires a very specific sample preparation method. You cannot use any sample in it because this is based on blinking of molecule. So let's say these are the two dots. Now, conventionally, if if we don't know whether these are two dots or not, we may not be able to resolve it. But let's say these are the two dots, and it's impossible to resolve it because of the optical diffraction limit. So how to do it using a storm? What we are doing it, we are basically making it dark. So we have a laser, very high power laser 647, which basically pushes this to a dark state and then excite the molecules separately and plot the center. Oh, sorry.
So I was about to ask you a question here. So is it possible, because the resolution main problem is that the two point source, we cannot differentiate between them as 2 point source because of the array disk, they actually merge at one point of time because of the diffraction limit. Is it possible that we have a point source or light source so precise, so thin that it actually illuminates one point as a like?
That is also there. You are absolutely right, but that's also a problem. There is a limitation of even the light spot also.
Okay.
That is also a big challenge.
Like there is no such light in the market which can actually illuminate one dot at a time.
No. So the procedure to do that is, so actually what is happening? Your question is very good. So why we are unable to resolve? Because the intensity of light, which is basically restricting us to separate those two dots, because the light is too much, right?
Yes.
So let's say in these two dots, the light is too much. So that's why we are unable to see what is happening in the background. So we just see one blob of.
Yes, we have to actually differentiate these 2 points from the background, because if everything is the same, everything is illuminated, we cannot differentiate.
Cannot. Yeah. So what the process done in Storm is basically, so they just make everything dark, and they just the sample is prepared in such a way that blinking happens, and they just excite one molecule at a time, and this is called photo switchable dyes. So we have to use a special process when we are talking about photo switchable dyes. So the concept of photo switchable dyes is means it can be on and off, on and off. So, and this process is long. It takes time to capture a storm image, and one image is basically around 3 or 4 GB. So excite one molecule separately and plot the center. So we have excited this one. First, we made it to dark. Excite one, plot center. Excite second, plot center. So now we can have two dots as a separate, right? Based on when we are blinking it, blinking the molecule. So it may blink again and again, but we have to take the peak intensity, Gaussian fit. We have to take the peak intensity in the consideration to plot the center. That is done by the software.
Now, many times, these two dots will blink together, but then there will be many times they will not blink together.
Correct. So that we call it as a non-specific activation. So the software will reject that automatically if it is together or.
Yes, so two dots next to each other blinking to same time, it will not record that, or
Correct.
it will actually.
We call it as an NSA, non-specific activation.
Okay.
Yeah. So just a minute. So then by this, we can separate out these two, and we have to repeat this procedure many times to create a super resolution image. Maybe it takes maybe 10 minutes, sometimes 15 minutes to create one image. So it's a tedious technology, but getting very popular because it is giving the resolution what is being required today. Because the biggest drawback in SCMs and all is there is no fluorescence capability, and there's no light cell capability. And this gives you that capability to perform even light cell also with that kind of a resolution, right? So let's say, for an example, this is my sample. Inactivate everything, dark state. activate. Few will get activated. This is basically stochastical activation. Stochastical. So some will blink, some will not.
Yeah, it's a random
Excitation,
process. Yes.
random, correct. Excitation will happen. So it will record. If it is repeated, it will not record. It will take once, right? Then it will again bring back to the dark state. So it is plotting a center, and this repeats 10,000 times or more, and then it will create an image. So it is something like there is an activator and there is a reporter. This is an antibody. So we have to prepare the sample in such a way. So there is a proper protocol to perform the sample preparation of STORM. So the combination currently is 405, 647, Cy2 647, and Cy3 647. So 647, Alexa 647 is a reporter die, and inactivate reporter molecule with 647. So let's say when we eradicate the laser, it inactivates, right? Excite the activator molecule to energize the reporter. It's sort of a fret, right, to ready state. So excite the reporter, light is captured by the camera. So 670 there, and then the camera excite the light. So basically, in a nutshell, you need to switch off everything, stochastically excite, and plot the center of those dots. So if you see this mesh, microtubule mesh, it is not resolvable. Using a storm, this is such a nice image. So these kind of things you can perform. So you can do multicolor using a storm, and storm image always will be a dot, 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 dot. It will not be a, like, we can't consider storm as a beautiful image tool, capturing tool, but it is more informative. It is more quantitative, like resolution wise. So that is there. And this is how it looks like a storm image, but you can resolve it much better. This is how a storm image. Now, storm can also be performed in 3D. That was 2D. Now, how to perform 3D? What we are doing between the camera and the objective, we basically insert a astigmatism, a cylindrical lens, to create an astigmatism. What I am doing, basically, I am creating a aberrations, a deliberate aberration. Means, let's say, because 50 nanometer is a very, very small resolution. So, to recognize which is above and which is low, we have to do something so that the lower molecules, a lower sample which is there, it should have a, let's say, for an example, if we say a below focus will be a sample which is vertical. Above focus is horizontal. Why it is happening? When we are putting in a cylindrical lens to create a astigmatism. This is how we can recognize which is above and which is low, because the resolution is quite low, 50 nanometer. We just can't see and imagine that this is above and below. So we have to have a cylindrical lens which is creating astigmatism, and then create a. So if you see the vertical ones, they are the below focus, and the horizontal one is the above focus. This is a mesh, and this is how you can create a 3D image using a storm. And so these are certain papers published using a storm already, and a very effective technology. And in India also, we have quite a good installation base of this. But the biggest thing is sample needs to be prepared very, very efficiently. Usage of storm is very simple, but sample preparation is the key. So this is the all storm papers. So how it performs, like it's an XY is 20 nanometer and Z is 50 nanometer. So you can perform up to 3 colors, 500 frames per second is the capturing capability. Yeah, this is all about today's topic. Any questions, sir?
No, no question from my side. Students, I know these super resolution and other things. I have not taught you people. This is more intense. But tomorrow when you come here and Mr. Tanwar will be here. So I'm pretty sure we are not going to do this super resolution and all. It is for your information. But I guess all of you know the basics of fluorescence microscopy and confocal microscopy. I have also taught, and you have now listened from him. There is always some jargons which will be there, but I think tomorrow when you'll be firsthand be in front of the microscope, you'll see how it works, and there will be samples which we will be imaging, and you will be sitting there, and and also there is a big part played by the software. It is not like a regular microscope in your laboratories which you regularly use. So I think there will be a big difference. So I'm looking forward to tomorrow's session, and please make sure all of you are present. So I think Mr. Tanwar, you'll be here around 10 o'clock.
Yes.
So we'll have a quick tea break, and then we can start around 10:30. So I expect all of you to be present in CRF around 10:30. Okay.
Sure. Yeah.
So we can close today's session. And thank you all. Thank you, Mr. Tanwar, for your time. Thank you.
Thank you. Thank you. Bye-bye. Bye.
Yeah. Mr. Arvind, you can close it.